To further illustrate this, I'm just going to make up a frankly ridiculous distribution. And this is what it looks like. No chance of a result below 0. No chance of a result between 1 and 3. No chance of a result between 4, well, above 4. And between 3 and 4, it's this constant density height of 0.5. And between 0 and 1, it's constantly increasing density. So it's much more chance of a result close to 1 than there is close to 0. We can see that that's a valid density function. It integrates to 1 because I've got a rectangle of height 1/2 and width 1. That's area 1/2. And I've got a triangle of height 1 and base 1. Area of a triangle 1/2 base times height for a right angle triangle. So that says area 1/2. So if I want to work out the cumulative probability, 2 points of it are quite easy, or 2 regions are easy to work out. No chance below 0, and certain if I'm into the region larger than the largest possible value. Well, let me integrate this triangle part. Integrate between 0 and 1. When I work this out, I'm integrating a linear function, a straight line, so I'll get a squared term, a parabola. Now, if I've got between 1 and 3, how much of the probability density have I already amassed? Well, I've amassed the entire triangle between 0 and 1, which is 1/2 of the area, but no more. So if I'm between 1 and 3, I've just got the 1/2 I've already amassed for the triangle, and then I start amassing probability density again as I move forward. So I've got the 1/2 I've already gone past the triangle, plus how much more as I move across the rectangle. So if I plot this admittedly crazy distribution up, it'll look like that. Nothing below 0, then this parabolic, this squared term between 0 and 1 until it reaches 1/2. Then it flatlines at 1/2 between 1 and 3 because there's no more density to accumulate. Then it starts going again, but this time at a straight line increase because I had a constant height of probability density. So when I integrated the constant, I got a straight line term, a linear term, until it reached all of it, until it reached 1, then it flatlined again. So again, I could simulate realizations from this crazy distribution by drawing points uniformly between 0 and 1 and reading off where they were. Now, inverting this function is not easy, but if I look at the 2 regions where I could simulate an outcome, i.e. between 0 and 1 or between 3 and 4. If I pick a point that's in the first half, so between 0 and 1/2, then I need to invert 1/2 z squared. So the inverse of squaring something then halving it is doubling something and square rooting it. So the inverse is the square root of 2z. And in the latter half, if I pick a point that's in the rectangle at the end, then the inverse of subtracting 2 then halving is doubling then adding 2, so I get 2z plus 2. I've maybe been a little slack by including 1/2 in both of those intervals, although given that this is a uniform point I'm selecting, the probability of hitting exactly 1/2 as the point I want is vanishingly small, so in reality it won't matter, but I've been a little bit slack maybe. So what I would do is I would draw a uniform point and then I would read off the inverse according to this rule. Now that admittedly is about as messy as these things get. A further example is, well, I say a less commonly seen variable. It's more commonly seen than that crazy example I made up on the previous slide. But it's not one of our standard distributions like a Bernoulli, binomial, geometric. A little bit more complicated, and that's a Pareto variable. Now this is named after Vilfredo Pareto, who was an Italian economist, and it's used to look at very skewed data sets. So ones where most of the values are close to the smallest value I might detect, but there are very large outcomes which are unlikely to be seen, but not impossible. They will exist. So it's used a lot in things like natural disasters modelling, where the chance of an earthquake happening is very small, but the consequence of it is very large. And this is used a lot in the insurance industry. Most of the insurance claims might be somebody's scraped a bit of paint off their car, or there's something which it happens every day, but doesn't cost very much to sort out, versus the cost of dealing with an earthquake. It's very, very uncommon that it happens, but when it does, the cost of it is huge. It also exists in nature, where we've got these size distributions of creatures. If you go into the oceans, for example, there's loads and loads of zooplankton for each small fish, loads and loads of small fish for each medium fish, ... and basically one whale for each however many billions of zooplankton. But in fact, the larger animals are much less common in number, but their size is much greater. And even amongst the annals of mathematicians with good beards, that is a good beard. So the Pareto distribution relies on two parameters, alpha and m. So the m parameter has a fairly easy interpretation. It's just the minimum value that gets recorded by this distribution. So that's why it's useful in things like insurance modelling. There might be a smallest claim that they pay out, or in ecology, a smallest creature that will be detected. So this is drawn a little bit exaggerated. In reality, the drop-off is probably very, very steep. But there's no chance of a value below m. There's no maximum possible value, but the larger and larger values I'm considering, the less and less frequently they will be observed. So it drops away constantly. So I can show it's a valid density function by integrating it and showing it integrates to 1. So alpha m to the alpha over y to the alpha plus 1 integrates to alpha m to the alpha over minus alpha y to the alpha. Evaluate that between the two limits, and I get 1. I'll work out the cumulative function by just integrating the density function between the smallest possible value, m, and the point I'm interested in, y. Now this is an integral with respect to the dummy variable t. So alpha m to the alpha is a constant, so I may as well pull that out the front of the integral. Now when I integrate the 1 over t to the alpha plus 1 with respect to t, put through the limits, tidy this up a little bit, and what I will get to is I'll get to 1 minus m to the alpha over y to the alpha. I can do a few sense checks that if I put through the smallest possible value, y equals m, then I'll get 1 minus 1, so I've got 0 density already accumulated at the smallest possible value. That's right. And then as y tends to infinity, then this thing will tend towards 1 minus 0, so it'll tend off towards 1, which is what I want. But we're talking about simulating values here, so if I want that, I need to invert that cumulative function. So the way I would invert 1 minus m to the alpha over y to the alpha, well, I rearrange it, I can get m to the alpha over y to the alpha is 1 minus f. So then if I just divide both sides by 1 minus f, multiply both sides by y to the alpha, then what I want now is I want y to be the subject of this, so I just need to take the alpha-th root of both sides, or raise both sides to the power 1 over alpha. So the cumulative, the inverse of the cumulative is m over 1 minus y to the 1 over alpha. So if I wanted realizations of a Pareto, I'd just draw uniform points between 0 and 1, and I'd calculate m divided by 1 minus my uniform point to the 1 over alpha.